Hi students, now in this lecture we will discuss about the working of a galvanic cell, how we generate the electric current from a galvanic cell, how it works, right? We know a galvanic cell is a device in which chemical energy is converted into the electrical energy, and the chemical reaction which actually is going on in a galvanic cell to produce current, that is called as a redox reaction, right? And a redox reaction we know is the one where one substance gets oxidized, okay, one substance gets oxidation, okay, so another substance gets reduced, so the other substance gets reduced. So that means in oxidation, in a redox reaction, oxidation and reduction is going on, right? So what oxidation is? Simply it's the loss of electron, right? We can say the loss of electron is an oxidation and the reduction is the gain of electron. So in a redox reaction, one substance loses electron and another gains, so that means one gets oxidized, another gets reduced, and this can happen hand in hand. Oxidation is only possible when the other substance can get reduced, so reduction is possible only when the other substance gets oxidized. To understand it, let's take an example. Suppose I have a beaker which contains for example the copper sulfate solution. So let's take the copper sulfate solution, aqueous solution of the copper sulfate, and in this one I want to dip the zinc rod here. So once I insert the zinc rod in the copper sulfate solution, a redox reaction will occur, right? Here the zinc substance gets oxidized and the copper from the solution will be reduced. So the basic reaction which occurs in this vessel once I insert the zinc rod in the copper sulfate is that the zinc loses electron, so the zinc, it will change into the zinc ions, the zinc 2 plus 2 electrons. So that means the zinc gets oxidized, and the copper ions from the solution, you know, the copper 2 plus ions from the solution, they will gain electrons from the zinc, and the reaction which occurs here is copper 2 plus ion accept the electrons which are lost by the by the zinc and form the copper solid here, okay. So when this reaction occurs, you know, one substance we find that gets oxidized here. So the zinc is getting oxidized, so this is the oxidation which occurs at the zinc, and the copper, it gains the electron, so that means it undergoes reduction here, okay. And overall this is the redox reaction, and when we balance it, when we add the two reactions, we can find the net reaction is like this. You know, the zinc, it reacts with the copper ions, okay, and the zinc loses electrons, form with the zinc 2 plus ions, and the copper ion accepts electron, form with the copper solid, right? So we can see the zinc, it gets oxidized, so this is an oxidation here, okay, and the copper undergoes reduction here, okay, so it gains electrons, so this is the reduction. Both reactions occur in the same vessel, that's called as a direct redox reaction. If both reactions occur in a one vessel, so this is a direct redox reaction. If you now suppose if I carry out a redox reaction in the two separate vessels, right, so that is a indirect redox reaction. Direct redox reaction, both oxidation and reduction occurs in the same vessel, but now if I develop a mechanism so that one substance gets oxidized in the one vessel, another substance gets reduced in another vessel, right, so that there is transfer of electron from one vessel to the another vessel, right, so that will be called as a indirect redox reaction, and that is how actually a galvanic cell works. This is the direct redox reaction here. This is an example of a direct redox reaction, okay. This is the example of a direct redox reaction. But now I want to see what will happen if I separate the two. If one substance gets oxidized in the one vessel, another gets reduced in the another vessel, so that there is transfer of electron from one substance to another substance, and due to the flow of electrons you get the current, you get the electricity. Now let's take an example of the two separate vessels here. One containing the zinc rod in the zinc sulfate solution. So we have a zinc sulfate solution which contains the zinc rod. Another substance contains the copper rod in another beaker. So this is a copper sulfate containing the copper rod. So metal ion in contact with its own metal in contact with its own ions. Okay, so here we have a zinc metal in contact with its own ions. So now see, if you connect the two electrodes here, if you connect the two electrodes, you connect the two electrodes through the wire. Simply use the wire to connect the zinc rod with the copper. We'll find the zinc will lose electron and the copper will gain. So this reaction is actually spontaneous. As soon as you connect the two electrodes through the wire, electrons will automatically flow from the zinc to the copper. So zinc will lose electrons. That means zinc will undergo oxidation. The copper gains electrons, and that means copper undergo reduction. Right? So why the zinc loses electrons? So because zinc is getting oxidized, right? Okay. So what we find here, that the zinc rod, it gets dissolved in the solution and form the zinc ions here, and the electrons, they remain on the rod, and then they start flowing through the wire, and these electrons come to the copper electrode, and the copper ion from the solution accepts electrons and undergoes reduction. That means the reaction is this one: copper ion accepts electrons which are lost by the zinc and form the copper solid. And what we find, that you get a deposition of a you'll get a deposition of a copper on the rod. Okay, on the copper rod. So you'll get a deposition of the copper. So that means copper ions will deposit on the rod, while as the zinc rod will dissolve. So that means the mass of the zinc will decrease, right? So the substance, this is zinc, it as soon as it dissolves, so you can say that the mass of the substance, the zinc rod, will dissolve, will start dissolving in the solution. Now due to this the loss of electron from the zinc and the gain of electron from the copper, we can say that zinc undergoes oxidation. So this is basically the oxidation reaction, okay, which occurs in the one vessel, and another vessel which contains the copper rod in the copper sulfate solution, that undergoes reduction. Okay, so this loses electron, the zinc, it loses electrons, the copper gains electrons. Now the redox reaction occurs in two separate vessels. Due to the flow of electrons from zinc to the copper, we can see the current is developed, and the direction of the current will be opposite to the direction of flow of electrons. Okay, so we get the current. But now when when one substance gets oxidized, we know that an electrode where oxidation occurs, that's called as anode, and reduction which undergoes reduction, that's called as a cathode, that I have discussed in the previous lecture. Anode which undergoes oxidation, anode is the electrode where oxidation occurs, and the cathode is the electrode where reduction occurs. Therefore the zinc, since it undergoes oxidation, will act as anode, and the copper, which acts which gains electron, undergo reduction, so that will act as a cathode. Okay, now see, if you connect the two electrodes, what happens? Electrons are flowing from the zinc to the copper, but what we find, that this current, the cell will not give current after few minutes. As soon as you connect the two electrodes, the current will be generated here, but then just after few minutes you will see that the cell stops giving current. This reaction will no more be spontaneous. Okay, why this cell, this galvanic cell, will not produce current? Why you get a current only after up to few minutes only? After that the cell will stop giving current, by this way, by this mechanism. If you take zinc rod in the zinc sulfate solution, copper rod in the copper sulfate solution, and then you connect it, you will get the current, but that current will stop after very short time. Okay, short time period. So maybe few minutes after, you will not get the current. The cell will stop giving current. Why so? What is the reason, right? The reason is because if when oxidation occurs in the anode, the zinc dissolves in the zinc sulfate solution. Initially, at the start, the solution was neutral. It contains the same number of zinc ions and the cations and anions, right, and the sulfate and the zinc ions. So the solution is neutral. But once the oxidation occurs at the anode, the zinc ion concentration will increase in the solution. So overall, the solution gets positively charged, right? it gets a positive charge. It was neutral at the start, but now when the zinc rod starts dissolving in it, the zinc ion concentration in the solution will increase, so overall the solution acquires some positive charge, right? At the same time, you see here the copper ions, they will gain the electrons, right? So therefore the copper ion concentration will decrease. When the copper ion concentration decreases, the sulfate ion concentration is more now, okay? That means the solution acquires some negative charge. Due to the positive charge here in the zinc and the negative charge in the copper sulfate solution, now this positive charge in the solution here, it will not allow the electrons, it will pull the electrons to go to the cathode, it will not allow the electrons to flow. And similarly, the negative charge over here in this solution, the kind of a negative charge we get in the solution, that will not allow the electrons to come towards the, so that is why, you know, the current will stop, okay? As soon as the sufficient amount of charge is developed in the two electrodes, the zinc electrode and the copper electrode, the current will stop, you know, the cell will stop giving current. So no more reaction will be now spontaneous. Okay, so therefore for this cell to produce a current for a longer period of a time, what we need, okay, we need to develop a mechanism so that the two solutions are kept neutral, okay? If you want to get the galvanic cell to produce a current for a longer period of time, we need to develop a mechanism that can keep the two solutions neutral. That means we need to neutralize the positive charge that is developed in the anode and the negative charge that gets developed in the cathode. And for that purpose, we use a salt bridge, okay? We use the salt bridge. Salt bridge is a U-tube which contains some electrolytes, some inert electrolytes, like it can contain the potassium nitrate, okay, or potassium chloride or sodium nitrate. So the main functions of the salt bridge are, first is it completes the inner cell circuit, second it keeps the solutions in the two half cells electrically neutral by exchanging its ions, the zinc ions, the excess zinc ions and the sulfate ions. In return, it provides its ions here. So if it provides the cation, if it takes cation here, in return it gives the anion, right? Okay. So here also the sulfate ions, it exchanges the anion with this cation here, so that the two solutions are kept neutral, okay? It also prevents the diffusion or the transference of the solution, right, from one half of the cell to the another half cell. Fine. So next point here is, how do we represent actually an electrochemical cell? How can we represent an electrochemical cell? As I said before, that an electrode where oxidation occurs, that's called as an anode, and the cathode is the one where reduction occurs. And when we represent a particular electrochemical cell, a particular galvanic cell actually, right? So what we do, we write down the vertical lines which represent nothing but the salt bridge, and to the left side of this salt bridge here we write down the anode, and to the right side of here we write down the cathode, okay? So these two lines are, this is a salt bridge here, okay? So I'll write down the anode from the left side and the cathode on the right side. So in this example, I have a salt bridge and the zinc electrode acts as anode, so I'll write down it from the left side of the salt bridge, and the copper acts as a cathode. So that means I'll write it on the right side. So this is how actually we'll represent it. So salt bridge, okay, these two lines, this is the salt bridge, and anode from the left side and the cathode from the right side. And when I represent the anode, I'll write down the metal in metal ion solutions, like this, metal by metal ion solutions, and also represent the concentration also, you know, the concentration of the electrodes. And the second thing, you know, the cathode, for the cathode I'm going to represent it by the metal ion positive, then the metal. That's where you find here the copper first, copper 2 plus by the copper, and here the zinc and the zinc ion. right? So this is how actually we represent an electrochemical cell. Vertical lines representing the salt bridge, left side anode, right side cathode, right? And anode by metal in the metal lines, this is how we represent, and the cathode metal line and the metal, right? This is how we represented the electrochemical cell. So hope you got the concept. Thanks for watching the video. Bye for now.